Yeah, so hi, welcome to my second lecture in the START series. The title is very interesting, Unveiling New Findings Going Beyond the P-value Hype. So basically, today I'm going to talk about the most important thing in statistics, it's P-values and significance. Like, if you know famous American writer, he once said that there is small lie, there is big lie, and there is statistics. And I fully agree with him. I think it's said that Mark Twain said it, but I think it's not his original citation. It's someone that before him said. So basically, yes, the largest lie is statistics. Why? Because we only can predict something based on statistics, based on probability theory, but we don't know anything for sure. So it depends how we interpret our results, how we present our results, and which modeling we choose. It's affect what we're going to tell to our like readers or whoever will sharing our results. And it basically depends on what we actually do. So p-value, significance, and hypothesis testing is one of the most crucial part of statistical theory. And if we understand it correctly, it will be easy for us to do the best research we can. So the objective of this lecture basically to explain what I just talked about. So in one of my first lectures during Lunch and Learn, we talked about sample population and philosophy of statistics. So we know that it's very hard for us to do analysis or do survey on full population. So we need to do sample. I think the only population level in Canada is census, when they ask basic question almost to everyone. But in real life, we cannot do anything with full population and we need to sample. But if we're sampling based on our sample, we only can infer what happened in the population based on our research or our modeling. So also in my second lecture, I talked about different types of uncertainty. So there's like types depending on how we collected the data and about our own opinion, but statistical uncertainty is actually literary uncertainty. It's the uncertainties that come up from measurement, how we measure things, and also from sampling, which sample we pull from our population. And unfortunately, with this uncertainty, there's nothing we can do. We can improve our data the best way we can. We can contact all the researchers and clinicians and ask the best way how to create our outcomes. But due to the nature of the sampling, we always have some kind of uncertainty. And actually the p-value and statistical tests that we do, they're trying to minimize the uncertainty and they're showing our results within the concept of the statistical uncertainty. Also, I talk about two main principles in statistics. It's homoscedasticity and heteroscedasticity. Basically, we can have two types of samples where our points in our sample are very close to our mean. It means that our variance across all the points will be constant, or where variance, we have a lot of points, but where our variance about our mean will be very distorted. And this is important later when I'm going to talk on variance or standard error and standard deviation to understand this. So the statistic part dealing with modeling, it's inferential statistics. So inferential statistics, as I said, use random sample to draw some conclusion about population. We draw the sample from. Typically, as I said, it's hard to obtain data from every member of population. So instead, we collect the random sample, a small part of the population, and from the sample, using different statistical procedures, we can infer the likelihood of some property of some event in our population. So hypothesis states that it actually really relates to inferential statistics. What is hypothesis testing? It's a vital process of inferential statistics where the goal is to use sample data to draw conclusions about the entire population. In the testing process, we use significance level and p-values to determine whatever test result are statistically significant. So basically, main statistic, all the papers we do for all of us is very important to get something that's statistically significant. But later I'm going to explain why it's not so important. So first I want to talk about basic statistical measures, and we probably all know about those. So there is statistical measures, the measure center of our data. And those are mean, median, and mode. We all know about it. But here I want to say that there is mean for our mean of our population and mean of our sample. And you can see there, usually in statistic population mean, it's used as mu, is Greek letter mu. And mean sample, it's x, where we have different point of x. It's kind of x with the line. And it will be our very average of our sample, and they never will be the same. So median, you know, usually it's 50% of the sample is in this number, and mode is it's most frequently repeated values in the sample. In addition to center of the data, we have spread of the data. Spread of the data usually measured by standard deviation for the population or standard error for a sample, and they're not the same. So basically, as I showed prior, we can have is the small disparity in the data, so where our points are very close to the mean, and we probably will have smaller standard deviations down arrow, or we have points that go far away from the mean, when those will be much larger. In addition to standard deviation and standard error, we can talk about interquartile range. So basically, you know, we can divide our sample based on median as like 50%, but you have 25% of the sample and 75% of the sample. It's usually say Q1 and Q3. So difference between Q3 to Q1, it will be interquartile range. Here I want to say I had a lot of questions about it when I did the analysis. People ask why interquartile range is not reported as range. It's usually never reported as range, it's reported as difference between two. It's actually one number. So talking more about standard deviation and standard error, if you look on the formula of in the right corner, you can see that standard deviation for population usually used as sigma. It's a bit different from the standard error from the sample. And the only difference in population we divided by n, number of people or subject in the population. And for sample, it will be usually n is number of people or subject in the sample minus 1. So standard error for our sample is measuring accuracy in which sample distribution represents population. So it's kind of approximation of standard deviation of the population. But I'm going to elaborate about standard error a little bit later, because it's very important measure for understanding statistical significance and p-value. And usually we say, if as more data we have, as larger sample we have, the smaller our statistical standard error will be. So basically, it's kind of very hard to decide. We can spend a lot of money, have huge sample, and have really small standard error, but usually we don't have it. We sample much smaller number of subject or events, so usually our standard error will be not very, very small. So additional important measure of statistics is degrees of freedom. What is degrees of freedom? You saw in the previous slide, when we calculated standard error of sample, we didn't use n as number of subject in the sample, we used n minus 1. Why? Because in order to sample us, we don't usually know all the measures in the sample, and basically definition simple definition of degrees of freedom is how many subjects or events we need to have in order to calculate everything in our sample. So in statistics, it indicates the number of independent values that can vary in analysis without breaking any constraints, or this is the number of independent values the statistical analysis can estimate. So here I did a simple example. Assuming we had order of 10 different numbers, we calculated the number mean of those 10 at 6.1, and we accidentally deleted the last measures x, and we close our computer. Next day we open our file and we don't have any idea what x was. But because we know the mean and we know total from additional 9 records in our data set, we actually, based on those first, can calculate x. So it means we had nine rows in our data set, but we use 10 rows in a data set, but we use 9 to calculate the missing number. This will be our degree of freedom. And if you're doing different tests, for example, for one sample test, we know that degree of freedom will be n-1. If you're comparing two independent samples, it will be 9-2. And for chi-square and b number of rows -1 multiplied by number of columns -1. And each test will have different degree of freedom. And this, for example, will be very important. For example, if you consider h in your model, if you use h is continuous variable, you will not lose many degree of freedom to estimate additional things. But if you decide to use categorical variable, because you divided your h by group, you will going to lose degree of freedom, and it can affect your sample power, sample calculation. You can lose the power in your calculations, and it can affect the statistical results. So it's very important to understand what degree of freedom is when you're choosing variables and type of variables you want to put in your model. So this, I don't know if a lot of people know, but basically, if you know center points or our distribution as mean, mode, and median, we can establish how skewed our distribution is. And usually there is a rule in statistics, it's called empirical relationship. We know that mean minus mode in slightly skewed data will be equal 3 multiplied by mean minus median. And here I give the example. For example, you can see on the left corner the symmetric distribution where mean, median, and mode will be the same. If it's positive skewed, you will have mode below median, and after that mean. And if you have negatively skewed distribution, so it will be mean, median, and mode. So by using the central measures of our data, just by calculating them, we will know approximately how skewed our sample distribution can be. So now, when we learned a lot of what's going to the model and what we measure, I'm going to explain how can we test hypotheses. So basically, in this lecture, first I want to explain classical approach of testing the hypothesis with the example, and after I explain that it's not what we think. So basically, when you start working on hypothesis, it's what's most important is to understand your data. So it doesn't matter what you do, you first need to learn your data and do descriptive analysis. Descriptive analysis is not going to help us to do inferential analysis, but it's going to help us in the future understand relationship in our data. So what can be included in descriptive statistics? We can describe our sample size, we can describe center measures of our data, mean, median, and mode. We can establish type of distribution, if it's symmetric or non-symmetric. We can use mean, median, and mode to see how skewed our data is. And here I want to say, if you report, you probably all know it, when we report mean, we need to report mean plus minus standard deviation. And if we report median, we need to put interquartile range in the brackets, because we want to see in which range our mean or median are in. We can, when we're doing descriptive analysis, we can identify outliers and decide what to do with them. We can review how many missing values there are in the sample and decide if we want to impute. And usually in this stage of descriptive analysis, we can compare our data, our main outcomes of varying variables in the data set by specific groups. And usually if you write paper, it will be table 1, yeah, description of baseline characteristic by some kind of groups. So after you do all the descriptive statistics, you actually can go and start your inferential analysis. So hypothesis test is the most important process in inferential statistics. So in descriptive statistics alone will help you to understand the data, but you cannot from it understand the relationship between sample and population and infer any trends or events from sample to population. And here I want to get back to statistical, to standard error. Standard error, what is standard error? I said it's a proxy for standard deviation of the population. But here, bear in mind, the sample error is a gap between sample statistics and population parameters. Yeah, so we're kind of trying to predict something from population, from something in population from sample. But unfortunately, and you can understand it, we never know what the values in population are. Whatever our population is unknown, because it's why we didn't do analysis on full population. We decided to do it on the sample, and we're trying to approximate our sample to our population when actually we don't know anything about the population. We don't have population mean, and we don't have distribution of the events in the population. So standard error basically measures something that we don't know what we're measuring. And it's directly related to p-values, because even we have the largest sample possible, like our population is million, we took 900,000 people out of the population, almost all population, we still do not know what the values in population are, because we only measured in 900. So our standard error probably will be very small, but the part between, because we don't know what happened in the population, we still have some kind of level of statistical uncertainty because we sampled. So here I can give you some examples. For example, survey company collected data from random sample in 2022 and learned that average amount of the family of four spent on food per week is $300. After that, the same company decided to do the same survey in 2003, and the answer was 445. So we see that there is increase in average amount of money that family spends on food. But it can be that there is inflation and prices went up, so the average price for food went up. But it also can be that because we did different sample, yeah, and because of the sample error, it's now 445. So, for example, if you sample exactly the same people than before and after, we can compare each family how much they spend during 2 different years. But because in 2022 and 2023, the survey company, for example, used different sample, there can be actual difference in amount of money the family spends on food, or it can be only because we choose a different sample. So basically, if we sample a lot, we can have 100 samples from the same population, and when we do analysis on different samples, we're going to get different results from the same model just because of the nature of the sampling. So here's actually example from one of my papers that never was published, but it was actually good. So basically, we try to estimate we created 4 different trajectories of using methadone for preventing overdose in the population, and we identified 4 different groups: slow increase in frequency of use of methadone, large decline, moderate, and stable frequency. And on the right side, you have actual. So basically, for each 4 groups, I divided my population I calculated of probability of people to be included in this group. But after that, to ensure that my results are stable, I did bootstrapping. So basically, I sampled 1,000 samples with repetition from the same population, and I put on the left side results of bootstrapping. Although the difference between those points of 1,000 samples are not very big because it's in scale from 0.9 to 1, we can see that still we don't get, there are some distributions now in posterior probability just to the nature of resampling 1,000 samples. So now I'm going to take what is null hypothesis. We always say, oh, we rejected null hypothesis, we accepted null hypothesis. So null hypothesis is a type of statistical hypothesis that proposes that no statistical significance exists in the set of given observation. So we say that something is not significant. For example, if you compare a mean of two different populations, usually our hypothesis, null hypothesis will be mean in population 1 equal to mean in population 2. Hypothesis tested is used to assess the credibility of hypothesis by using samples. So we're doing from sample. In simple word, in scientific research, the null hypothesis, often detonated at H0, is the claim that no relationship exists between two data sets of variables. So it's what I said. We usually say two averages are the same or something else is the same, and we're trying to prove that by H1 hypothesis, by alternative hypothesis, is actually it's not correct. So there is an additional term we need to understand. It's significance level. So basically it's detonated by Greek letter A, and it's called, in other words, called type 1 error. So basically in research, especially in medicine, we usually use type 1 error at 5%. So p-value less than 0.05%. It defines how strongly the evidence received from the sample are contradicting the null hypothesis before we reject it. Or it indicates that there is 5% risk that the effects exist when it's actually not existing. So basically, null hypothesis, so basically when we reject null hypothesis, we calculate in the false positive. So how many times we can reject the hypothesis when it's actually was true. Yeah, so basically it's our error. We say, oh, actually, the means in our samples are the same, but we rejected to say it's not the same. So there is another type of error. It's usually detonated by beta. It's type 2 error. It's error of omission. So basically, errors that occurs, we will fail to reject null hypothesis when it's actually need to reject. So basically, it's our false negatives. So here are some examples. A man came to the doctor, and the doctor said, oh, sorry, you're pregnant. And pregnant woman came to the doctor, said, oh, you're not pregnant. Yeah? And here you can see the table gets actually, it shows you when we accepting the null hypothesis correctly and when not. So if null hypothesis is true, and in reality is true, and we predict it true, the accuracy will be 1 minus alpha, and between null hypothesis and alternative hypothesis will be better, and so on. So the happy phase means that we predicted it correctly, and the sad phase will mean that we predicted it incorrectly. And here is also examples that you have distribution of first null hypothesis and alternative hypothesis. This will be 1 minus alpha and 1 minus beta, and those in green and blue, it's actually our alpha and beta. And we use those distributions statistically to decide if we predicted our hypothesis, if we rejected our hypothesis correctly or not. So basically, this is where we know if p-value is less than alpha 0.05, we reject the null hypothesis, and if it's more, we accept the null hypothesis. So here I give small example of hypothesis testing. It's classical. I'm using binomial distribution here. So example is in supermarket, came to scrutiny, said the bags you're using, they tear apart if you put more than 5 kilo in it. So, and the store did the check and said out of rumble samples of 200 bags, 185 did not serve when they put more than 5K in it. And we can ask question, like theoretical question, can the supermarket claim at 5-level significance that more than 90% of the bags will fall apart? So our null hypothesis actually that our P proportion of the bags that tear apart is less than 90%, and alternative hypothesis will be that it's more than 90%. So our probability of bags to tear up will be 185 divided by 200, it's 0.925. Using binomial distribution, it was my previous lecture. You can listen on it online when it's available. Based on this one, we calculate standard error of the sample. Yeah, and using the test that statistics, we can estimate with a level of significance of 0.04% that our Z is 104, and we can say that based on the test we did, there is no enough evidence to claim that at 5-level significance, that more than 90% of the bags will not fall apart when carrying more than 5 kg. So it's basically the simple example of if you in start class receive something how to do the hypothesis testing, this is usually what you're going to do. So now I'm going to, so this is classical kind of example of how to test hypothesis, but now I'm going to tell you what I'm thinking about null hypothesis. So I treat null hypothesis as devil advocate position. So I say it's never true. So it assumes that whatever you are trying to prove me will never happen. So, and this example, to prove it, I can give you imaginary experiment. Assuming we wanted to compare two drugs and we say one drug should perform better than another drug, but my mistake, we give everyone a placebo. Yeah, so we have treatment and control group, but both groups receive placebo. So because both groups receive placebo, if we are assuming that there is no placebo effect, and the placebo effect that there's a lot of talk in research is zero, we should not have any difference between drugs that we give to treatment group and drugs that we give to control group. But actually, if we use it on the sample, in the end, there can be situations when we actually receive some kind of unexpected effect. We shouldn't, because we know both groups give the placebo, so both groups we give exactly the same. But actually, when we did our hypothesis test, we could see that there is some kind of effect. In this case, we will not expect any effect, as we actually did not administer the actual drug for sake of this imaginary experiment. Despite the null, so this means that even we know that we shouldn't have the difference, we can still get the difference, and it will be kind of our probability of reject or accept null hypothesis. Despite the null being accurate, we will likely, so I'm summarizing in the slide, that despite the null hypothesis is accurate, we will likely observe an effect in the sample data due to random sampling error, our standard error. The sample values will never be exactly equal to the null hypothesis value. Whatever we do, we will never get, from our sample, we will never get a result that equal to values in our null hypothesis. And the devil advocate, my position in this case will be random sample error produce the observed sample effect. It is not an actual effect, yeah, of this treatment, as we did not expect any effect due to administering placebo to both groups. So what is actually a p-value? In this case, p-value will indicate my belief in the devil advocate case. So p-value actually my belief that the null hypothesis is correct given the sample data. So basically p-value can measure the degree of agreement between our statistics, so sample statistics, and the null hypothesis. assuming that null hypothesis is right, what is the probability of, so it's kind of assuming that we know that null hypothesis is right, what is the probability of obtaining the effect at least as larger as 1 in your sample? So basically it's what p-value in this case will be. So assuming the null hypothesis is right, what is the probability of obtaining the effect at least as large as 1 in the sample? And high p-values, your sample results are consistent with null hypothesis, and low p-values mean we reject the null hypothesis, is inconsistent. So what is perception of p-value? Yeah, so now I'm going to say why p-value is not good as we all think. So one of the most significant issues with p-value is widespread misinterpretation. Many people mistakenly believe that p-value tells you the probability that null hypothesis is true, and this is not accurate. Yeah, it's not what it means. It's actually instead it measures the probability of absorbing data as extreme as results obtained, assuming the null hypothesis is true. So if we have misunderstanding what p-value is, we kind of can misinterpret our results and make a wrong conclusion from our calculation or from our hypothesis testing. So in my opinion, the p-value does not measure the probability of the null hypothesis being true. P-value assumes that null hypothesis is true. So we only assume it's true. As I said, as a devil advocate, I say it's never true. P-value indicates how compatible our data is with the assumption of statistical modeling, including the null hypothesis. So as I said before, we use a sample, we can use multiple samples, and for each sample get different results. So, and it only shows how our specific data, our specific samples that we choose with our assumption of statistical model. We are not establishing the truth with hypothesis testing. We cannot say that something is true or something is not true. We test to see how much support we find for alternative hypotheses. Yeah, so basically if we so basically when we're doing the hypothesis analysis, both null hypothesis and alternative hypothesis are important. And I showed if this diagram true and false, they actually related. If we reject one, we accept another and opposite, and we can do mistakes in both. So when we say p-value less than 0.055%, given that the null hypothesis is true, we will get the results like the one we observed or more extreme away from the null and average, no more than 5% time of the chance. So basically 0.05 measure a percentage of times on how many times we reject the hypothesis when it actually was true. So what additional perception of p-values that maybe is not true? It's threshold-based thinking. Researchers often use significant threshold to determine whatever the results are statistically significant. So this is kind of binary approach, is it significant or not significant? And this can lead to neglect of valuable information. An example, like only recently more papers that didn't get significant results are published. Yeah, before, like if you try to publish paper and the results are not significant, it will be really hard to justify. But actually in your results where they're not significant, there may be much more valuable information. So it's not straightforward that if something is statistically significant, it's good. Yeah, and also if you do an analysis, statistical significance and p-value can be dependent on your sample. If you have very large sample and very small difference between mean of two variables, for example, you can get significant results. But the question is it meaningful to get results at 0.1 different? Is this meaningful for us even the results is so statistically significant. You also can have opposite. You actually get your sample is decent and results are very close, but they will be not significant. As again, I say it's only due to nature of the sample because we sampled. Because as I said before, when you're doing hypothesis testing, by standard error, we're trying to predict something we actually don't know. So reproducibility issue, p-value, as I said, p-value is sensitive to sample size, and small sample size can lead to unstable and reliable results. So in the fields with small sample size and complex experiment setup, for example, I work in genomics, that you have huge line of different genes with very small sample, it will be very hard to get statistical significant results. Maybe the results are correct and meaningful, but because the sample size, for example, is very small, but you have a lot of columns in your data, a lot of variables, it will be very hard, almost impossible to get significant results, but you still can do your research. Publication bias. Researchers and journals often prefer to publish studies, as I said, with statistically significant results, leading to publication bias. And only recently people start talking and more papers with not significant results are published. Also, for example, we know that most of the studies in social science, I don't know about medicine, but my background was mostly in social science in the beginning. It's very hard to replicate the same results. You can do psychological experiment on other experiments with different groups, and it will be very rare that you get exactly the same results in other group. For example, an example from medicine that I really remember, I learned it in one of the courses I said, in Australia, they did machine learning experiment, and it was all over the news because they say they identified genes responsible for autism. Yeah, but later, a group in the UK, I believe, tried to look on it, and they did different experiment. Actually, they found an error in Australian paper because they training and tests and training sets were overlapping. But actually, when experiment on different sample was done in UK, they didn't get the same genes. So until now, I don't believe anyone can predict genes that are responsible for autism in children. Yeah, so, but because the results were so good and so statistically significant, everyone talked about it, but actually it was untrue just because the way the results were presented. Additional perception of p-value. What we think about p-value, it's inadequate control for multiple comparisons. So, you know, you're trying a lot of things, you're doing different tests, but actually it's correct, because if you're doing multiple statistical tests, you need to adjust your p-value. Yeah, usually it's like if you did 10 tests, you need to divide your decided p-value of 0.05 by 10 and compare with the new p-value because you did multiple tests. Lack of context. P-value do not provide information about the practical or clinical significance of the effect. A statistically significant result may not be practically significant or vice versa. So when we get in statistical results and we get in something statistical significant, we need to understand in clinical settings if it's actually is meaning the statistical results. If the difference between two treatments at 0.01 is significant, is actually it's clinically important. Maybe it's not. It's statistically significant due to nature of our sample or how we did our experiment, but it's actually clinically completely irrelevant. So alternative method, I'm not sure I 100% agree with it, because I'm not a big fan of Bayesian methods, but actually they say if you imply Bayesian methods, and Bayesian methods are basically built directly on 3 axioms of probability theory. Yes, so some say there is debate in statistics that say, oh, if you get Bayesian statistics, it will be more informative and you can describe your results a better way, because Bayesian methods allow researchers to update their beliefs based on prior information. So when you're doing Bayesian predictive model, we always need to define our priors as come from some kind of distribution. And because we use a priori, it will be much easier for us to incorporate it in uncertainty and have more explicit results. Dependence on assumptions. P-values are usually calculated based on several assumptions, and it's including an assumption of independence. So usually when we do something, we're comparing something, we assume that events or samples are independent. And we also know that the data can follow particular distribution. So basically, if we violate the assumption of independence, or we misinterpret distribution or use different distribution, we can get the maybe correct but completely misleading results. And I have this a lot when I get requests, a lot of linear regression. So people come to me and say, oh, we're going to do linear regression. But in order for us to do linear regression, we actually need to check if assumption for is to imply linear regression model are correct. Because if our assumption of linearity are not correct, we can run a linear regression and put it in ROSAS and get some kind of results, but results are being misleading because actually the relationship between our y and x, between our variable and our outcome, maybe not linear. So we need to look into it. For example, I recently wrote a grant about angles in ultrasound. Two papers that I found related to the subject, they all the papers in the subject were showed as linear relationship. But mathematically, when you measure angle, it's actually a cycle. So in order for you to do the analysis of ultrasound angles, it's actually better to use circle distribution. So I still can go and run, go run my linear model and get some results and write some graphs and present the results and describe results, even do discussion. But actually, whatever I'm going to do, it will be wrongly because I use the wrong distribution that's not relevant to specific data or specific research questions. So what we can do actually to deal with this p-value. So basically, again, I always say about it, it doesn't matter generally for me how big your sample is or how small your sample is. Big, of course, larger sample, of course, is better because we're looking on standard error and trying to predict something we don't know. We always have the level of uncertainty that kind of can be transcribed to our interpretation of p-value and our significance. So what we can do, so for example, we did our research, we got our results, and they're statistically significant, and we are very happy about it. What we need to do? We can, for example, look on effect size as measure of intensity. Effect size quantifies the magnitude of an observed effect rather just statistical significant. Common effect size can measure by Cohen's data that for comparison of mean, it can be odds ratio for binary outcomes and correlation coefficient for relationship between variables. For example, in study comparing two treatments for medical condition, Cohen D could be used to measure the difference in treatment outcomes between two groups, providing more practical sense and effect size. So how Cohen D is usually calculated, it's different in means divided by full standard deviation. And full standard deviation, it's square root of square of first standard deviation of first population plus second population divided by 2. As for statistical significance, if you calculated Cohen D and calculated the effect size for your sample of your research, we can, based on the cutoffs for effect size, you can know what's going on. For example, it's if your effect size is less than 0.2, it indicates a small or negligible difference between groups. If it's between 0.2 and 8, it suggests a moderate difference. and if you got effect size of 0.8, then it indicates substantial large difference. So for example, if you did your research and you got statistically significant results, but you also got a decent effect size, if you could calculate it, it proves that your results are more robust and more solid. So basically, effect size allows to compare the size of effect across different studies or experiments and help you to assess the practical significance of differences that you observe. So also, we know when we report something, we always report confidential intervals. So what is confidential intervals of, we say, 95% confidential intervals. Because we have p-value of 0.5% to reject the hypothesis when it's actually true, there is 95% actually to predict it correctly. So when we say the mean for our sample is this and that within confident intervals, we know that between minimum and maximum confident intervals, we're actually confident that our results are correct. So for example, you can have situations that your results are statistically significant. For example, you calculated confidential intervals for odds ratio. Your results are statistically significant, but and your results are 0.2 in odds ratios, but your confident intervals are between 0.8 and 2.5. Because confident intervals is included in one, you are not so confident that actually results is 1.2 you received. It's actually a meaningful result, despite the result be statistically significant. So when you looking on your results, you are not only looking on p-value and your actual output, you also need to consider confident intervals, how confident you are in your results. So for example from the literature, 90% for confident interval for mean blood pressure reduction due to a new drug will be between 5 mmHg to 10. Yeah, so when you report results, it's very important to review your results based on confident intervals and also look on the clinical significance of your results, if it actually makes sense. So additional techniques that I personally really like, I use it a lot, is bootstrapping. What is bootstrapping? You have your original sample and you want to validate your results are robust. You resample, usually based on original paper of Efron. It's usually good to use 1,000 samples, and if you need, I can send you to station. So you resample from your sample 1,000 samples with repetition. You allow the same person to be in the sample multiple times. And after that, you run your analysis on full sample or bootstrap sample. This way you get more, because your sample size right now is some 1,000 times larger, you will have the smaller standard error, is that will give you more narrow confident intervals. So your results will be more conservative. For example, if you got statistical significant results using your original sample and statistical results by significant conservatively using your bootstrap sample, it means your results are robust. Also, you can calculate results, as I did this example from my paper. You can calculate the results for each specific sample and plot it and look at what is the distribution of your final results based on samples. So basically say, yes, we know that we can have different samples, and due to nature of our sampling, we introduce uncertainty and standard error, and it's really affecting our significant level. But if the results from your samples are really close, you don't have it all over the place, it means that you did a good job and your results are robust. There can be situations when you did bootstrapping and actually you will get opposite results. So for example, in your original sample result was statistically significant, but using bootstrapping, you can get not statistically significant results, and your results from sample will be all over the place. It may hint that maybe you didn't do a good model, maybe different models should be used. So you didn't check all the assumption and you need to check your work, or maybe this is the nature of your sample. And it's usually good to report your actual results and results for bootstrapping. Yeah, that is it from me. Any questions? No questions? Did you understand everything I was talking? Because I understood, but like if I understood, it doesn't mean that everyone else will understand. But basically, the main point of this lecture, when you do something and it's statistically significant, before you jump in, oh, it's glad how good it is, we did a good job, you need to validate that actually your results are robust and you actually understood what you did and why it's statistically significant. And again, as I said, it's very important to use descriptive statistics, because very often when you get your statistical results, the statistical results from the model and significant, when you look for your descriptive statistics for different trends and combination of the data, it actually will make sense. But if you did descriptive statistics and it doesn't, descriptive statistics, different frequencies or simple relationship, and you look in for your model, it doesn't make sense why it's happening, like why you have the discrepancy on you, and you don't understand the connection between your descriptive results and your inferential analysis, you might need to check yourself and see again your modeling and do. And I didn't add here, if there is no question, usually when you do the modeling, in addition to statistical results, you need to look for model fit statistics. It's actually, if it actually makes sense. And if you want to choose best model, you're trying to do backward selection or stepwise selection or sensitivity analysis when you're removing and adding different outcomes and trying to figure out what is the best model. It's very important also to look for fit statistics in addition to your significant results. That is, thank you.
So we have a question from the class.
Yeah.
Okay. So with regard to you said we have to adjust the p-value for doing multiple different analysis on the same sample. What did you mean by that? I didn't really understand.
No, so sometimes you doing different tests. Yeah. I usually don't do multiple tests. But if you're doing multiple tests, yes. So for example, you did your analysis and you run 10 different models. Yes. You cannot use p-value of 0.05 because each model is different. So usually you need to reduce for more conservative results. But I personally rarely do it. I always, when I do the analysis, I usually do statistical analysis plan on modeling and how I'm going to check it and how I'm going to do the modeling. And I usually doing it once and get my results. Because if you're trying to alter your model and trying to get best results, I call it monkey business. Yeah, you're trying to get something that you want, but that maybe it's not actually there. So I suggest really before you're doing the modeling to see about the models, to check your assumptions, to do all the work to make sure that you don't need to do multiple tests. If you want to read about it more, it's called Bonfiore adjustment. One of the simplest way to adjust p-value for multiple tests, it's called Bonfiore adjustments. And in my next newsletter, I can write more about it, like put more details about how you adjust to p-values for multiple tests.
Thank you.
Thanks. Okay, so the next lecture, I don't remember what it will be. I think it's odds ratios, relative risk, hazard ratios, because I learned that a lot of research is confusing, like comparing proportion, odds ratios, hazard ratios. And so I'm going to do description of those, what it is, and show maybe some modeling of tests, how to present those results and how to do different comparisons and what it means. Okay, have a nice weekend. Bye.
Bye, thank you.